Marseille, south of France, for those of you who don't know. I'm going to argue in this talk that one needs to have multiple progenitor channels for type 1a supernova in order to explain the full range of observed properties. And most of you in the room are probably comfortable with the idea that there could be multiple progenitor channels for these events, but maybe only a fraction of you are actually convinced that this has to be the case. And so the argument is based on fairly simple physical arguments, but they're backed up with relatively complex radiative transfer signatures. Just like to thank my collaborators who this out at Nice Observatory, John Haley in Pittsburgh, and Alexei Kopkov in Chicago. And I have almost as many sponsors as this conference, so I'm pretty proud. So we all know that it's actually difficult observationally to constrain the progenitors of type 1a supernovae. You can't detect the actual white dwarf that explodes, but even the binary companion often eludes detection. Even in the best case scenario, this 2011 FE, in pre-explosion image we just don't see a companion. So most of the time, well, we have to rely on indirect observational constraints, where there's the early post-shock breakout luminosity, we heard a bit about that yesterday, interaction with the binary companion on the CSM, people that look for surviving companion stars in remnants, people also run population synthesis calculations to compute rates for different progenitor channels. So this is actually an ideal situation where one really needs numerical simulations to inform these observational constraints. But even then, numerical simulations also have a hard time distinguishing between different progenitor channels, and this is again taking 2011 FE as a test case. This is drawn from a paper by Frisoko collaborators, where they consider these two models, so a single transect mass white dwarf and a double white dwarf merger. And we know that these, both of these progenitors are fundamentally incompatible one with another, yet in early times, the single transect mass white dwarf seems to do a better job in terms of the synthetic spectra that are produced, and at later times it's the other double white dwarf merger that seems to match up well with the observations. So that's telling us that either the radiative signatures of different progenitor channels is too small, in which case it will always be very difficult to tell the difference, or the uncertainties in the modeling is still too large. We also know observationally that there is a diversity in the type 1a supernova population, the most obvious of which is the factor of 10 variation in peak luminosity. But also at a given peak luminosity, here shown on the right, two objects have very similar light curves in the B band and have display subtle differences in terms of the spectrum here, just illustrated using the width of the silicon line. So this observational diversity could be explained in various ways, but one way to explain this is to have these multiple, to allow for multiple progenitor channels and or explain mechanisms. So this is the work that I do with my collaborators. This is the kind of setup that we use to simulate these objects and predict their radiative display. So we start off typically with an idealized textbook white dwarf, carbon oxygen, hydrostatic equilibrium. Then the explosion phase is followed in 1D until the ejector reach a ballistic regime, so molecular expansion, less than 1 minute after the explosion. And the output of the hydro calculation is basically a density profile, a velocity profile, abundance profile, which can be fed into a radiative transfer code, for which we use the CMF gen code of John Haley that was originally developed for hot star winds, but has now for more than 10 years been applied to supernova. So again, it's a 1D code, which can be considered as a limitation in itself, but the fact that it's 1D allows us to treat various physical processes. In particular, it's a fully non-LTE code. It includes all the time-dependent terms in the radiative transfer equation, the statistical equilibrium equation, the energy equations, all of which are coupled explicitly. It treats non-local energy acquisition by gamma rays and also non-thermal processing. And so the output of these calculations is basically a time sequence of spectra, which can then be directly compared to observations. You can see they can directly be compared to spectra, but even if we want a light curve in some band, we simply integrate our output spectra over a given filter. So that's the setup, and we showed in our first paper on type 1a supernova, we considered a grid of transect mass data condition models where we tune the transition density between the initial evaporation and the subsequent detonation in order to produce a grid in nickel 56 mass. Basically a factor of 4 difference between the most, so 0.8 solar masses of nickel 56 down to 0.2 solar masses of nickel 56. And that allows us to have a leverage on the peak luminosity, and we're able to, for each of our models, to find an observation that matches up well at that luminosity, even down to the least luminous 91 G line. This is a maximum light only, however, but so to confirm a specific model, one really needs to look at the full evolution from early to late times. So if we look at this, this model here in more detail, so this is a model with 0.5 solar masses of nickel 56 compared to this 2002 BO. In terms of the pseudo-bolometric evolution, you can see that the luminosity evolution is well matched by this model. Same for the spectra from 12 days before maximum out to 56 days past maximum light. Yeah, there's obviously a slight mismatch here at early times, but nothing to write home about. What this tells us is that the chemical stratification of our input model is probably close to what is actually happening in nature. However artificial the 1D explosion is, this really tells us that real or more elaborate explosion models should produce a similar kind of chemical stratification in order to reproduce the observations. This is a 1D curve, so it's spherically symmetric. We see that even under this assumption, we're able to reproduce the spectroscopic evolution at least up to the first 100 days past explosion. So we know that we expect the explosion to be intrinsically asymmetric and to have large-scale mixing and all this. It doesn't seem to affect, at least at the level where we can tell the difference, the rate of display. One thing that I'd like to stress is that there's no fine-tuning along the way. So we start with initial conditions that are less than 1 minute after the explosion, and then the ejector basically evolved they're evolved without adjusting the abundances, the densities along the way, and we're able to go from 1 minute to 100 days after explosion. So we have this grid of Sham-Shaker mass delay detonation models. Obviously, the natural thing to do is to see what these like on the width, the Phillips relation, with luminosity relation. I've never heard Mark call it the Phillips relation, so I'll stick with luminosity. So I'm going to, these are data taken from Hickett et al., Tau and Becker et al., peak V-band magnitude versus delta and 15, and we're going to see where these models lie on this relation starting from the most luminous to the least luminous model. This is where our first model lies. Okay, so the peak luminosity is right on the relation. Peak luminosity is right, that's no surprise, we know the nickel 56 mass. So we expect it to be, in this case, a luminous event. But to get the decline rate correct for this luminosity is another thing that's very sensitive to the color evolution around maximum light. So it actually comes as a pleasant surprise for it to match up so nicely. So if we keep going, see the second least more luminous model also follows the relation. It's starting to, you can see it's maybe slightly steeper than the observed relation, but it's certainly in the right direction. This is our fifth model, so it all seems to work pretty nicely. So at this point, my collaborator is and I, we're happy people here. And I'm assuming Mark is also a happy person here. And for that matter, I guess Nick is also a happy person here, although some might argue that on this picture, Nick doesn't look genuinely happy, but he's at least as happy as this guy here. Look at the similar kind of expression. Okay, back to the Phillips relation. So the next model, you can see it starts to drop off slightly, but it's still within the scatter, so it's nothing to worry about. Now this, you can't argue that it's just scatter is just completely wrong. The next one is just completely opposite. So our happy moai is turned to skeptical moai. This is this guy here, and our not so happy Nick is also turned to skeptical. And again, note the similar gestures and facial expression. Okay, so this is one model grid, Chandrasekhar mass delay detonation model. So we can see we've tested other Chandrasekhar mass models, pulsating delay detonations. This is where they lie. It's the same story. The most luminous models follow the relation, and then it kinds of drops off to follow an anti. with luminosity relation. So basically the fainter chandrasekhar mass models, they decline too slowly for their luminosity. The luminosity is correct, we just want to move all of these points over here. So if we look into more detail what's happening, let's say with our least luminous chandrasekhar mass model, well, you can see that the peak luminosity matches, this is compared to the 91 PG like 99 dy. The peak luminosity matches, that's basically set by the nickel 56 mass, here's 0.12 solar masses. You can clearly see the light curve, the luminosity evolution is too slow. In terms of the spectra, here at maximum light in 30 days data, you can see that the spectra are clearly, the synthetic spectra are clearly too red at maximum light and still somewhat too red 30 days later. So these chandrasekhar mass models, they're too broad, they have too red colors. In terms of, if you want to look at colors in B minus V, yeah, it's not a small difference, it's up to 1 magnitude, too red a few days before maximum light. So we want to find a way of having the same peak luminosity, but having faster light curve evolution, and to have bluer colors at maximum light. So physically what this means is that we want a timescale for radiation to escape to be shorter, the luminosity evolution to be more rapid, and we also want a more efficient heating of the ejector for the same amount of nickel 56 that will affect the colors. And one way to do that is to consider lower sub-chandrasekhar mass models of good. And that's kind of displaced. Okay. Okay, so if you lower the white dwarf mass, you're considering lower density progenitors, and therefore you're allowing the radiation to escape more freely. Basically, the Blondin depth is also lower. And the fact that you have a higher nickel 56 to total mass ratio means that the heating rates per unit mass, so the specific heating rate, will also be higher. And so we'll have a more efficient heating of the ejector for the same amount of radioactive input. And so what we consider are these sub-chandrasekhar mass models that have been around, but they've not really been around for a long time, where a sub-chandrasekhar mass carbon-oxygen core creates a helium layer which detonates at some mass. I put 0.2 solar mass as an upper limit. We know from calculations of people in this room even that this helium shell can detonate in much lower masses. This is just for illustrative purposes. When this helium shell detonates, helium burns explosively and produces this outer shell of ion group elements, and then can drive a secondary detonation in the carbon-oxygen core, either directly or indirectly by conventional heating. So the advantages of such a model is that it naturally explains the absence of hydrogen or helium in the spectra. You only need a moderate accretion efficiency to get this build up this helium shell, as opposed to the single degenerate scenario. There's no deflagration to detonation transition mechanism required, which is still a poorly understood mechanism. And there we have a natural parameter that determines the nickel 56 mass and hence the peak luminosity, and that's the white dwarf mass. And the predicted rates are also higher. There's a fundamental flaw to this model, that's this outer shell of ion group elements, which is just fundamentally incompatible with observations. We know that the early time spectra is dominated by intermediate mass elements and not by ion group elements. So that's actually a serious problem, but my collaborators and I, we actually found a neat way around this problem, that was to ignore it. And so we ignored the helium shell altogether. It works every time, you should try it out. By ignoring the helium shell, we're effectively considering pure detonations of low mass carbon-oxygen cores, and in that respect, it's very similar to the setup that CIMIT in 2010 uses also. So if we look at these models in a little more detail, so we have a chandrasekhar mass model here in red and dotted line. 0.12 solar mass is nickel 56, chandrasekhar mass. And we look at its sub-chandrasekhar mass equivalent in terms of nickel 56 yield. So you see it's the same nickel 56 mass, but the total mass is lower. You can see from the density profile that this is 1 day past exposure, you indeed have a lower density throughout the ejector. And also if you look at the nickel 56 distribution, you can see that nickel 56 extends a lot closer to the actual surface of the white dwarf than in the chandrasekhar mass case. And both of these actually enable both radiation to escape more freely, and also gamma ray escape to set earlier on at a higher rate. And again, the higher nickel 56 to total mass ratio, which is given here, is roughly a 50% larger ratio, leads to a more efficient heating of the ejector per unit mass. So in terms of the bolometric evolution, this is what happens to these two models. So it's the same nickel 56 mass. So this dotted curve here, which is the decay luminosity, applies to both of these models. But you see that the subtranslucent mass model peaks slightly earlier and has slightly higher luminosity. That's basically because it's, this Pinto Eastman 2000, it's radiating the same amount of luminosity just over a shorter time. So it peaks earlier on and it's slightly higher luminosity. And you can see the gamma ray escape fraction sets on earlier on at a higher rate. So let's see how this model compares to the low luminosity 91 BG-like events. This is what we have for the Schramm-Shaker mass model, so a two broad light curve and the two red spectra. Now for the sub-Schramm-Shaker mass model, you can see that the peak luminosity is roughly the same, and the luminosity evolution is now well matched. This is pseudo-bolometric luminosity. In terms of the spectra were too red, significantly too red at maximum light, and somewhat too red past maximum. And for the sub-Schramm-Shaker mass model, you can see that it matches up well, both at maximum light and 30 minutes later. So if we go back to the width-luminosity relation, this is where this Schramm-Shaker mass model lies in terms of B-band magnitude versus delta M15. And for the same nickel 56 mass, this is where the sub-Schramm-Shaker mass model lies. It's not quite there yet in terms of decline rate compared to the low luminosity events, but the key thing to note is the difference, the relative difference in delta M15 for the same nickel 56 mass. Here we have 0.6 magnitudes in terms of the B-band decline rate. And of course we didn't only compute a single of these models, we computed a whole grid, from the most luminous to the least luminous. The very low luminosity one here, which has 0.08 solar mass of nickel 56, also turns over to kind of an anti-relation. But up until to this point, you can see that it's only the sub-Schramm-Shaker mass models that probe this region above 1.4 in terms of delta M15. And below this cutoff value, if you will, there are both a mix of Schramm-Shaker mass and sub-Schramm-Shaker mass models. And so we might want to ask the question whether these sub-Schramm-Shaker mass models can actually also accommodate reproduce normal type 1a supernovae. So if we look into more detail at two models that have the same nickel 56 yield. This is the Schramm-Shaker mass model with 0.5 solar masses of nickel 56 compared to 2002 BO, which we saw earlier, so a nice match to the luminosity evolution and to the spectroscopic evolution. The luminosity evolution for the sub-Schramm-Shaker mass model with the same nickel 56 yield, this is what it gives. I mean, it's equally good. In terms of the spectra now, at maximum light it does a fine job. At past maximum light, so this is again 30 days past maximum light, you can see that the sub-Schramm-Shaker mass model is clearly too blue. In terms of B minus G color, this is half the magnitude too blue. The colors match up nicely between both models at maximum light, and they correspond to the colors of 2002 BO. But then our sub-Schramm-Shaker mass model just fails to get red enough. Basically, it fails to cool. We can see this from the temperature profiles at maximum light for both models. They're very similar at maximum light. This solid dot is a kind of a characteristic location for the spectrum formation region. The temperature profiles are fairly similar at maximum light. 30 days later, you can clearly see that the sub-Schramm-Shaker mass model stays significantly hotter in the inner ejector where the spectrum starts to form at these times. And the reason why the sub-Schramm-Shaker mass model fails to cool is because of its lower density. So the lower density basically inhibits all of these cooling processes that scale as density squared, and the model stays hot for longer. And so we have this situation where we've just seen that now the sub-Schramm-Shaker mass model, although they follow the width-luminosity relation, their colors at 1 month past maximum are incompatible with observations. And here we saw previously that the Schramm-Shaker mass models were incompatible because they are too red at maximum light. And then we have this intermediate gray zone there where it's unclear which fares better. So let's actually see what's going on in this gray zone. We have a model with 0.4 soda masses of nickel 56, the Shannon mass model, the sub-Shannon mass model compared to 1992A. It's difficult to say which model is best in terms of their luminosity evolution. And same, even in terms of the spectroscopic evolution, around maximum light 30 days later, maybe the sub-Shannon mass model does a slightly better job here compared to the Shannon mass model. But then, one can argue that the Shannon mass model does a better job at reproducing this cachito here. Okay. So you have in this gray zone, it appears that both the Shannon mass and the sub-Shannon mass models are compatible. At lower decline rates, high luminosities, only the Shannon mass models appear to be compatible. At larger decline rates, low luminosities, only the sub-Shannon mass models appear to be compatible. So the width luminosity relation is a great tool to calibrate type 1a supernova peak magnitude. It's also a great tool to do type 1a physics. And we wouldn't have been drawn to investigating this further hadn't it been for the mismatch that we saw in this relation. So this is my conclusion. So we just see that the standard Shannon mass models match the normal type 1a supernova fairly well, but they fail to match the least luminous events simply because they are too red at maximum light. Just the sub-Shannon mass models match the low luminosity events, but they fail to match the normal events because they are too blue past maximum light, so they fail to cool. And the reasons why one model fails and one model succeeds is connected in both cases to this specific heating rate per unit mass, which is scales as the ratio of the nickel 56 to the total mass. And these are really relatively artificial explosion models, but they certainly seem to indicate that there's a simple physical reason why one would expect a range of progenitor white dwarf masses to explain the full range of observed type 1a supernova properties. And I just end by saying that all these are published model inputs, so in terms of the hydro inputs and also the synthetic spectra are publicly available at this webpage, and I'm sure everyone's happy about that.
Stephane, very nice. A question, when you compare the volumetric light curve with, I think it was 99y, it says beta I. Is the model also beta I?
It's basically the pseudo-volumetric luminosity using BVRI magnitudes, so integrating BVRI fluxes.
But it's over the same wavelength, right? Just what you said.
Yeah. For both the models and the observations, yeah.
So first, Stephane showed me these results before the talk.
I'm sorry?
No, I'm just saying.
Okay. Yeah.
It's very kind to show me the results before, so I had a question for them. At least according to your results, this is something I told you. You want a model with no helium, which has the mass of a sub-Chandra for the low nickel 56 mass guys, and has the mass of a Chandra for the high nickel 56 mass guys. This is just what comes out of the molecular calculations of collisions already in the field. So what is your comment? Can this be one model that explains all of this?
Yeah, it certainly could be. So you really you want a sub-Shannon mass ejector for these least luminous events, so you would have to have collisions of low mass white dwarfs, let's say 0.6 low mass white dwarfs. That certainly, it would be a more satisfactory solution to this as just computing these separate model grids and invoking these two quite different progenitor channels, which would somehow, as we discussed yesterday, magically know when to switch over from one to the other. So having a kind of overall framework in which would produce similar ejector conditions would be, of course, ideal. These models are artificial, and we're not pretending this is how they really explode, but they at least enable us really to test the impact of the ejector mass on the rate of display. And then from then one can use this to inform people who actually do explosion modeling in terms of the hydro simulations to produce ejecta that have similar properties in terms of total mass and nickel 56 field. So yes, certainly the collisions are definitely worth looking into.
Hello, I'm not sure whether you have done similar work for double weather model. If yes, where the model is located in your West luminosity
relation. Yeah. So that's an easy one to answer because we have not computed double white dwarf merger. Well, done the rate of transfer calculation for double white dwarf mergers yet. So I can't answer that question. So.
Similar to Kayla's, I mean, you've tried to convincingly show that there's two classes of more, and one skeptical one and one happy one, but I would also argue with the comment that I think it's a range, and I think also the Phillips relation or the width luminosity relation clearly shows that there's no real breaking there. So, I mean, can you make any prediction of saying like, having a feature that you would only clearly detect in one versus the other?
Well, there is one, but I don't know how far it applies to realistic explosion models. I mean, with 1D transfer mass models, one of their distinct prediction is the existence of this nickel 56 hole in the inner regions, which are then dominated by stable ion group elements, which does not exist in the lower density sub-transfer mass models. And so what you have at late times in the Shamsek mass model, we have some stable nickel that still survives in the inner ejectors, and you expect to have these very strong nickel lines in the nebular spectrum. In the sub-transfer mass model, all the nickel 50, essentially nickel 56 that was there has decayed to iron by the time you reach nebular times, so you wouldn't expect nickel lines, for instance, in the nebular spectrum. That's one signature. I've talked to people who do multi-D simulations for the explosion. They don't expect this nickel 56 hole to actually survive in multi-D calculations just because of the buoyancy of the hot ash. So that would be, if one detects nickel lines in nebular time spectrum, then that's a clear signature of stable.
You should detect them in some, but not in others.
Yes, in the Shamsek mass model you detect it, and in the sub-Shamsek mass you don't.
I mentioned in my talk, but as you said, the modern variants of the double definition scenario don't need anywhere near consensus or massive helium on top, so you can get by with thousands of different mass. When you do that, you don't produce any iron elements. It's all silicon and calcium helium. So you don't really have to ignore it. It ignores itself.
Okay.
They shouldn't have much benefit.
Okay. I was under the impression that even for the... leave it to the mic. Yeah, I was under the impression that even for these minimal shell models that, for instance, Fink et al. Considered, that they still had some titanium and chromium production, fairly under low abundance, but it does have quite a significant impact on the rate of display.
So there are reasons why the new was listed that helium shell detonation isn't right. So I'll show a lot of some work we've done.
Okay, cool.